Problem 4. Charge inside a hollow spherical shell of radius r equals to 4 meter centered at origin is defined as rho v equals to 0 for r less than or equals to 2 and which is equals to 4 by r square coulomb per meter cube for 2 less than or less than or equals to 4. The electric field intensity at any point in the region r less than or equals to 2 is. Solution. So let us observe, as per the problem given, here the volume charge density was defined for a shell. It's right. The shell contains a radius of r is equals to 4. Now we need to identify it. So we need to calculate what will be the electric field intensity for r less than or equals to 2. So what we do is, initially we will try to interpret how the spherical shell is. So the spherical shell has the volume charge density to different types of distributions. For r less than or equals to 2, it is 0, 2 less than r less than or equals to 4. Right. So for r in between 2 and 4, it is defined as r 4 by r square coulomb per meter cube. Now we need to identify what will be the electric field intensity for r less than or equals to 2 region. For easy understanding of this particular problem, what we have to do is we have to interpret how the volume charge density is defined for that particular shell. So for that, what I do is I will try to draw the cross sectional view of the spherical shell. So let us take, this is the spherical shell what we have with radius r is equals to 4. So let us take the spherical shell has radius r is equals to 4. Now how the volume charge density was defined? So for r less than or equals to 2, the volume charge density is simply 0. So what I do is I will take one more spherical shell up to r less than or equals to 2. So let us take, this is the shell what I am drawing for r less than or equals to 2. So this is r equals to 2. Now in that spherical shell we have 0 charge region. It's a 0 charge distribution, and so within this particular space what we have, the volume charge density is defined with that expression, that is 4 by r square coulomb per meter cube. Now as per our question, simply electric field intensity for r less than or equals to 2 we want. Electric field intensity for r less than or equals to 2, that is the electric field intensity within the inner shell what we are supposed to calculate. Just you observe, there will be no charge in this particular region. Since there is no charge, so easily you can say that it's immediately, whenever you observe the condition here which is given for us, that is r less than or equals to 2, since there is no charge within the region what we have, the electric field intensity is also equals to 0. That theoretically we can say, if you want, we can apply the Gauss law here, that is the total flux leaving through this particular shell which must be equals to the charge enclosed. Now if you are considering this one as the Gaussian surface, and if you are calculating the total flux leaving, then which must be equals to the charge enclosed as per our Gauss law. The charge enclosed within this particular shell is always 0. Right. So therefore the electric field intensity is also equals to 0. So by applying the Gauss law or by the observation, immediately we can say that the electric field intensity for the given condition r less than or equals to 2 is always equals to 0. This is our answer. Question number 5. Now for the same question which was asked in our previous problem, now we need to calculate the electric field intensity at r is equals to 3 meter. So this is a question which is given to us, that the charge distribution was given as rho v is equals to 0 for r less than or equals to 2 and 4 by r square coulomb per meter cube for 2 less than or less than or equals to 4. This is the problem. Now the same data was given to us once again. So this is the charge distribution which is given to us, and this is the spherical shell what we have with radius r is equals to 4. In that one, so rho v is charge distribution. Now we need to calculate the electric field intensity at another location, that is E at r is equals to 3 meter we require. In our previous case it is r is equals to 2 meter, since there is no charge it is equals to 0. Now we are supposed to calculate the electric field intensity at r is equals to 3 meter. Now once again try to interpret the data, by taking a simple pictorial representation of that one. So what I do is I will try to draw once again what will be the charge distribution with the help of two spheres. That is, let us take, this is r is equals to 2 meter sphere. Within that r is equals to 2 meter sphere, so there will be no charge, therefore the charge density is 0 in that one. And next r is equals to 4 meter sphere. So this is r is equals to 4 meter sphere. And so between the 2 meter sphere and r is equals to 4 meter sphere, we have volume charge density which is given with some expression. So rho v is present in this particular region only. Now what we have to do is we have to calculate the electric field intensity for r is equals to 3 meter distance. So what I do is I will try to take this r is equals to 3 meter sphere. Let us take this is r is equals to 3 meter. Now exactly at r is equals to 3 meter sphere we are supposed to calculate our electric field intensity. Now as I said, our Gauss law is very much useful law here to calculate it's anything. It's electric field intensity or electric flux density or whatever it may be. If you want to calculate that particular one, if we apply our Gauss law, it is very convenient to solve the problem. So what I do is I will try to form a Gaussian surface at the point what we require. So where we require. So here clearly at r is equals to 3 we are supposed to form a Gaussian sphere or a Gaussian surface. That Gaussian surface is nothing but the Gaussian sphere. So clearly take this particular dotted sphere as the Gaussian surface what we have. So this is our Gaussian surface, and clearly remember that this Gaussian surface is a spherical shaped form. It's a spherical shaped one, right? Now apply our Gauss law here. That Gauss law is nothing but the total flux leaving through the Gaussian sphere or Gaussian surface is equals to the charge enclosed within that Gaussian surface. So first what I do is I will try to calculate the total flux leaving through the Gaussian surface and I will make it equals to the charge enclosed within that Gaussian surface. So calculate the total flux leaving through the Gaussian surface. The total flux leaving. So flux leaving is equals to, how to calculate that one? Using its flux density. Take the flux density and as a substitute here. Then let us take the flux density is d, it's a integrated with differential surface ds. So clearly it is a closed integration. Since we are forming a closed Gaussian surface, it is a closed integration. Surface integral of d ds, that what we have. Now which is equals to, as we discussed, this d and ds will be in the same direction. That is d will be in the radial direction. ds also will be in the same direction. Don't go for any formula, just observation is required here. So whenever it is necessary, you will take the formula, right? D in radial direction, ds in radial direction, the dot product will be a scalar and here d is uniformly distributed, so bring it out from the integral. So clearly it is d surface integral of ds. So this surface integral of ds will give us the surface area of Gaussian sphere, that what we considered. This is a Gaussian sphere with radius 3. What is the surface area of any sphere? 4 pi r square. So simply substitute 4 pi r square instead of this total surface area of the Gaussian sphere, which is equals to d into 4 pi r square, which is nothing but r is a radius of the sphere what we considered. This is 3. So 3 square is 9, 9 into 4, that is 36. d 36 pi is the total flux leaving through the Gaussian surface. So till now just we calculated the total flux leaving through the Gaussian surface, which is equals to 36 d into pi. Keep it aside. Next calculate the total charge enclosed within that Gaussian sphere. So the total charge enclosed, Q enclosed is equals to, this total charge enclosed can be calculated using its charge density. The charge density which is given to us is 4 by r square from 2 to 4, and for r less than or equals to 2 it is 0. So if you observe that one, the charge is uniformly distributed for the region 2 to 4 only, and below that r is equals to 2 there will be no charge. And here we are considering the sphere, there is nothing but the Gaussian surface up to r is equals to 3 only. So we don't require any charge which is beyond this limit. So just you take the charge up to our Gaussian sphere, that is up to r is equals to 3 only we are supposed to observe. So clearly total charge enclosed will be calculated up to Gaussian sphere, that is the charge starts at 2 meter and ends at 3 meter. So the integration is also from r is equals to 2 to 3 meter. As we said, this is since it is a volume charge density, volume integral will be there. So just you leave the remaining 2, and what I do is for our convenience I will write that one as the volume integral. This is not the notation, but for our inconvenience I am writing like this: volume integral of rho v dv. For understanding I wrote the limits of r only. I left the limits of the remaining two parameters what we have, right? Now substitute here. So which is equals to r is equals to 2 to 3 meter, that what we have, and write down the remaining two limits also. The two limits which are meant for us are, theta is from 0 to pi and phi is from 0 to 2 pi. So I will write those two also, that is theta is equals to 0 to pi and phi is equals to 0 to 2 pi. Now replace our rho v with 4 by r square. 4 by r square multiplied with dv. We want differential volume in which coordinate system? It's a differential volume can be taken in spherical coordinate system. Since the particular quantity which is given is uniformly distributed in a sphere, we are supposed to take the differential volume in spherical coordinate system. So don't remember the equation of differential volume or surface. Once again I am saying, try to obtain that one in any particular direction or for a required quantity using a simple formula, that is nothing but the differential length. So what is the differential length in our spherical coordinate system? The differential length is equals to dr ar plus r d theta a theta plus r sin theta d phi a phi. So this is our differential length equation in our spherical coordinate system. If you want differential volume, just ignore the unit vectors and multiply all the parameters what we have. That the coordinates, so dr, r d theta and r sin theta d phi. If you multiply them, what we get is differential volume. So if you multiply, what we get is r square sin theta dr d theta d phi. Now here we are supposed to take those equations, otherwise it's not possible to solve this one. So 4 by r square dv here we have to write. So clearly substitute the dv also. Then q is equals to the integration for r is equals to 2 to 3 and theta is from 0 to pi and phi is from 0 to 2 pi. So if you multiply this one with this dv, r square will be cancelled. So the remaining one is 4 sin theta dr d theta d phi. Simply what you have to do is you have to simplify this one to get the total charge enclosed up to the Gaussian sphere. So clearly observe, we are calculating the total charge enclosed up to the Gaussian sphere only, right? So if you integrate this one dr, what we get is 3 minus 2, that is 1, and for d phi 2 pi minus 0, that is 2 pi, and 4 already we have, that's a constant, and sin theta d theta is minus cos theta is taken from pi to 0, therefore the answer what we get is 2. So here clearly after multiplication of this one, 4 into 2 8, 8 into 2 16 pi, so which is equals to 16 pi. So clearly observe here, just what we did is we calculated the total flux leaving through the Gaussian surface. Since we are supposed to calculate the electric field intensity at this particular region, I calculated the total flux leaving, which is equals to d into 36 pi, and the total charge enclosed within that one is 16 into pi. As per our Gauss law, these two are same, just make them equal. So if you make them equal, that is the total flux leaving is d 36 pi, which is equals to the total charge enclosed, which is 16 pi. Pi will be cancelled, therefore d is equals to 16 by 36, which is nothing but 8 by 18, that is 4 by 9. But clearly remember, this d is not a scalar quantity, it is clearly a vector quantity. We are supposed to represent its direction also. So clearly the d will be in the direction of radius. So with the observation directly you can write that one. So directly d can be written as d is equals to 4 by 9 in the direction of radius AR, just now I have added. But what we want is the electric field intensity, right? So clearly d and electric field intensity are related with one equation, d is equals to epsilon naught E. Since it is a hollow sphere, so here I am taking the epsilon is equals to epsilon naught. If we are taking any other medium, we are supposed to take the relative permittivity or the permittive dielectric constant of that particular medium. Since it is hollow sphere, I will take epsilon is equals to epsilon naught. So E is equals to, that is 4 by 9 epsilon naught AR. So this is the answer what we require. Yet R is equals to 3 meter. So at R is equals to 3 meter, the electric field intensity which is coming out of the charge what is given to us is 4 by 9 epsilon naught AR. Question number 6. For the same question which is given in our previous problem, if the region is outside the spherical shell, then what will be the electric field intensity at R is equals to 5? That we need to calculate the electric field intensity at radius is equals to 5 for the given charged shell. Now the same problem was asked, the same data was given, but here we need to calculate the electric field intensity at different location. So in the first case at R is equals to 2, in the next R is equals to 3, that in between the two spheres what we considered, we calculate the electric field intensity. Now beyond all this, that at R is equals to 5, what will be the electric field intensity we are supposed to calculate. So the same data was given. So what I try to do is, once again I will try to draw the sphere what we have with R is equals to 2. Let us take this is the R is equals to 2 sphere. Let us take this is the R is equals to 4 sphere. Now here we are supposed to calculate the electric field intensity at R is equals to 5. That radius is equals to 5 we are supposed to take. So directly what I do is I will try to apply our Gauss law here. So don't go for any other, just try to apply our Gauss law. So if you want to apply the Gauss law, once again we need to form the Gaussian surface. As the shape which is given to us is a sphere, clearly the spherical one is the Gaussian surface, that what we can form. So at R is equals to 5 meter, I will try to form a Gaussian surface. This dotted one is the Gaussian surface what we can form, on which the electric field intensity is uniformly distributed. So this is R is equals to 5 meter sphere. Once again the same principle is applicable here. Calculate the total flux leaving through the surface and calculate the total charge enclosed within that Gaussian surface. So this dotted one is the Gaussian surface. Once again clearly observe, we are calculating the total flux leaving through this one, that is the flux is going out. Next to calculate the total charge enclosed. Now equate them. How the total flux leaving through this one can be calculated? The flux leaving is equals to the same formula what we are using is surface integral of d ds. Since it is a closed surface integral of d ds we require. This d is uniformly distributed. Since it is uniformly distributed, bring it out. And the analysis is same. The d and ds both are in same direction, that is in radial direction. Since both are in same direction, the dot product will give us a scalar and the term will exist. And if you bring it out, that what we get is d surface integral of ds. This surface integral of ds will give us the total surface area of the Gaussian sphere. So here integral s ds can be replaced with the surface area equation. So what is the surface area equation of the Gaussian sphere? Once again it is 4 pi r square. So this can be written as d into 4 pi r square. So d into 4 pi r square is equals to, here what is r we are supposed to take? Radius of the Gaussian sphere what we took. Radius of the Gaussian sphere is 5. So instead of this r, if you substitute 5 into 5 is 25 into 4, 100 pi. So the answer is D 100 pi. This is the total flux leaving through the Gaussian surface. So clearly observe here, we calculated the total flux leaving through the Gaussian sphere using our flux density. Right? Now calculate the total charge enclosed. The total charge enclosed is equals to, once again this total charge enclosed can be calculated using its charge density. The charge density is defined into different ways. Up to radius 2 it is 0, and from 2 to 4 it is rho v. That rho v is given here. Right? So clearly from 0 to 2 no, nothing can be calculated, leave it. But from 2 to 4 we are supposed to calculate the charge. So within that particular Gaussian sphere what we have. So directly I am writing the integration for this charge in terms of its rho v. For r 2 to 4 we are supposed to take, because from 0 to 2 there is no charge density. I am taking r from 2 to 4, and for the integration 0 to theta is from 0 to pi and phi is from 0 to 2 pi. And what is the volume charge density? 4 by r square multiplied with its dV, differential volume equation. In our previous problem we gone through that one. The differential volume expression is r square sin theta d theta d phi. So clearly just what we are doing is, once again we are calculating the total charge enclosed within that Gaussian sphere. Now simplify this one. If you simplify, r square will be cancelled. So dr also will be there. Sin square sin r square sin theta dr d theta d phi. This is our dv. right? So after simplification, this r square will be cancelled. The answer may be 4. For d phi it is 2 pi. For dr, the upper limit is 4, lower limit is 2. So 4 minus 2 it is 2. And sin theta d theta. Sin theta d theta simplification is cos minus cos theta from pi to 0, that is 2. So this is the equation. That what we have is, once again check, this is 4, and for phi it is 2 pi. For r it is 4 minus 2, 2, and for sin theta d theta it is also 2. Therefore 16 into 2, 32 pi. So 32 pi is the total charge enclosed within that Gaussian sphere. So what we calculated, the flux leaving and total charge enclosed, make them equal. So therefore clearly we can write d 100 pi, that is the total flux leaving, which is equals to 32 pi, that is the total charge enclosed. Now if you take the equivalent of this d, then what we get? This is epsilon naught E 100 pi, which is equals to 32 pi. So if you take this one, then what we get is E is equals to, electric field intensity is now 32 by 100 epsilon naught. This is the scalar quantity, but what we have to do is we have to represent our electric field intensity as a vector quantity. Since it is a vector, we are supposed to add the unit vector in that particular direction. Already we observed that d is radially outwards. Since d is radially outwards, E is also radially outwards. So clearly write down E as a vector, that is E bar is equals to 16 by 50 epsilon naught in the direction of radius of the sphere. That is E bar is equals to, this may be, so 8 by 25 epsilon naught AR. This is our answer. So problem 7. The electric field intensity at a distance 3 meter above the center of a circular loop of radius 4 meter lying on the xy plane and carrying a uniform line charge of 3 nanocoulomb per meter as shown in figure is. Solution. Here just you observe in the problem, it is given a ring. It's a loop was given to us, and most fortunately this loop was placed on xy plane. So this is the case what we discussed in our Gauss law applications as a special case, that whenever we have a ring charge, that ring carries some line current charge density, that how to obtain the electric field intensity. Already we derived the equation of that electric field intensity. Now what we have to do is, we have to correlate that particular data what is given to us with that expression. So what I do is, I will try to get the equation for that electric field intensity because of a loop. So the electric field intensity is already known to us, which is equals to rho L AH divided by 2 epsilon naught A square plus H square whole power 3 by 2. So this is the equation for electric field intensity, so volt per meter. Now what we have to do is, we have to obtain all the parameters which are included in this formula from the figure. So the figure is given like this. Now observe. So what is rho L here? The rho L is nothing but the line charge density along the ring what we are taking, or what we have considered. So the line charge density is given as 3 nanocoulomb per meter. So that is rho L is equals to 3 nanocoulomb per meter, which is equals to 3 into 10 power minus 9 coulomb per meter. So instead of rho L, we have to substitute this one. Next, what is A? So in the derivation what we did, the A represents the radius of our ring. So here clearly we need to consider the radius of our ring, that is 4 meter. So consider A is equals to 4 meter. Next, H. H is nothing but the height where we are calculating the electric field intensity along z axis in that particular derivation. Here fortunately that is also coincides. Along the axis, at which height we are calculating the electric field intensity? At 3, that is at a height of 3 we are calculating the electric field intensity. Therefore H can be simply replaced with 3 meter. So substitution of all these parameters will give us, but here we require the direction of this electric field intensity also. That the electric field intensity magnitude I wrote here. What about the direction of that electric field intensity? Always remember the electric field intensity direction is along z axis. So we need to add the unit vector AZ. So if the ring is placed on any other axis, that according to that one we are supposed to take the axis direction. Let's say if it is placed on any other plane, we are supposed to take the direction of axis. Here the direction of axis is along z axis, therefore I am considering the direction of our electric field intensity in z direction. So substitute all these parameters here. Then the electric field intensity is equals to rho L is 3 into 10 power minus it is nanocoulomb. Since it is nanocoulomb, it is 9. 3 into 10 power minus 9 into A. A is 4 meter and height is 3 meter divided by 2 into our epsilon naught is 8.854 into 10 power minus 12. So that is the epsilon naught value. So A square plus H square. A square plus H square is 4 square plus 3 square. So 25. 3 by 2 under root 25 is 5. 5 cube. That what we get instead of this entire term. So this is simply 3 3 is 9, 36 divided by, here what we get is 2 into, approximately take this one as 9, 2 into 9 into 125. 2 into 125 is 250 into 9 into, here what we have is 10 power minus 9, here what we have is 10 power minus 12. So if it goes to up, it becomes 10 power 3. That what we get. So approximate equation you can write here, 250 into 9, it's a 250 into 4 is 1000, 9 is 2000, it is 2250. So 36 divided by 2250, that what we get here. So 2250 into 10 cube. So simply it is 3600 divided by 2250 into 10. So approximately equals to, that what we can write is an approximation 36 by 22. 36 by 22 is 18 by 11, which is equals to 1.7 into 10, which is 17 volt per meter. So clearly just up to this part, that what we have to observe, that we need to correlate the data which is given to us with the formula what we have, that E is equals to rho L, it's a line charge density which is given to us. Next, A is nothing but the radius of the ring. H is the height of the point where we are calculating our electric field intensity. The remaining is just mathematical equation, mathematical solution, that what we have to solve using our calculator. So this is 17 volt per meter is our answer. Consider the electric field intensity in some region is found to be E is equals to 3 r square AR volt per meter. The total charge stored in a sphere of radius 2 meter centered at the origin will be. The solution to this problem. Just observe what is the data given to us. Here the electric field intensity is given to us as 3 r square AR volt per meter. We are supposed to calculate the total charge stored at r is equals to 2 meter. Here clearly it's a spherical shell, a hollow sphere is given to us. We are supposed to calculate the total charge stored. So for that, so for our convenience, just you try to draw the cross sectional view. So let us take, we have a spherical shell. So the spherical shell radius is r is equals to 2 meter. So the radius of that spherical shell is 2 meter. So within that radius, how much charge was stored? That what we want, right? Once again, just you apply Gauss law here. Nothing more than that. If you take the Gauss law, then it is most easy to solve this problem. Using our Gauss law, we need to calculate the total flux leaving through this region. Once again, take this particular boundary as the Gaussian surface. So we are taking this one as the Gaussian surface. We are trying to calculate the total flux leaving through that Gaussian surface and calculate the charge enclosed within that one. How to calculate the total flux leaving? So once again, what we have is a basic formula that the total flux leaving is equals to integral d ds. So we don't know how much d we have, but we have E. This d and E are related. So what I do is, I will try to solve this one using this E. So how this can be written? So this can be written as epsilon naught E ds. So epsilon naught is constant. Since it is given in free space, that I took here epsilon naught. So epsilon naught is constant. Bring it out. So which is equals to epsilon naught E ds. So here E is available, but we don't know what is ds. Differential surface. This differential surface is obtained for, will be obtained for a spherical coordinate system for a sphere, that what we are considering, right? In the further sphere, in which direction differential surface is given? The differential surface is given in radial direction. So we are supposed to take the equation of the ds in radial direction. So for that, ds in radial direction we want. So how to represent, or how to write the equation for this one? Once again, take your dl equation. Differential length is equals to dr ar plus r d theta a theta plus r sin theta d phi a phi. This is the differential length equation. As I said, we can obtain the differential surface in any direction using this single equation. The differential surface in which direction we want? Radial direction we want. So leave this term and multiply the remaining two parameters what we have, that is r d theta, r sin theta, d phi. Clearly the differential surface in radial direction can be written as r into r square sin theta d theta d phi. So just it is an observation, and from that observation we took the differential surface equation. Now substitute E and ds here, then which is equals to epsilon naught. So what is E equation? It is just 3r square ar dot ar. Here the direction of differential surfaces also will be there, that is ar. So directly what I am doing is, I am trying to take the direct form. So ar dot ar now becomes 1. So directly I wrote 3r square multiplied with r square sin theta d theta d phi. So this 3r square into r square, initially I will write that r square sin theta d theta d phi. So instead of this entire dot product, what we get is this one, right? Which is equals to epsilon naught. Here what I do is, I will try to give you the simplest form. Here the differentiation is with respect to theta and phi only. So r term can be treated as constant. So here r square into r square, what we have is r power 4, that can be treated as constant. Bring it out, that 3 r power 4. Now the integration is for surface, that what we are considering. Now that integration will be taken for theta and phi only. To form a complete sphere, what are the limits of our theta? Theta limits are from 0 to pi and phi limits are from 0 to 2 pi. Just you write down those two, nothing more than that. Sin theta d phi. So simply the total flux leaving is equals to epsilon naught 3 r power 4. The limits will be taken from theta and phi only. Theta is from 0 to pi and phi is from 0 to 2 pi sin theta d theta d pi. Just integrate this one, that what we get is 3 r power 4 epsilon naught. If you take integration for this d phi, what we get is 2 pi, and if you take integration with respect to this theta, that is sin theta d theta, what we get is 2. Now simplify this one. So what we get is simply 12 pi r power 4 epsilon naught. Now at which location we require the electric field intensity? At r is equals to 2 meter we require the electric field intensity. So for a fixed value of r is equals to 2 meter. So what we get is here 12 into 16 pi epsilon naught coulomb. So this is your answer what we require. So the total charge enclosed, for the total charge enclosed, we are not calculating the total charge enclosed, just we are calculating the total flux leaving. That total flux leaving is equals to the total charge enclosed. Now the total flux leaving can be calculated using this simple formula. So if you simplify this one using our calculator, then this will be the answer. Problem 9. In the entire free space, electric potential is given by V equals to xy square z cube plus 3 by 2 natural logarithm of x square plus 2y square plus 3z square. The electric field and electric flux density at point P of 3, 2, minus 1 will be. Now here in this problem the potential is given to us. The potential is given in terms of x, y, z, that is clearly in rectangular coordinate system the potential function is given to us as xy square z cube plus 3 by 2 natural logarithm of x square plus 2y square plus 3z square. Maybe the units are volts. So here the potential is given. Next we need to calculate the electric field intensity at some point P in the free space. Right? Now how to obtain or how to relate the electric field intensity or potential? We have a very classical relation that the electric field intensity and potential are related with this equation E is equals to minus gradient of V. So if we apply the gradient on the V potential equation, then what we get is the electric field intensity. As we discussed, just this was given in a rectangular coordinate system. So this del operator will be considered in rectangular coordinate system. So what we do is just we will apply the gradient on this particular function. So if you apply the gradient on this particular function, what happens to it? Just observe. Minus. So this del operator can be expressed as dou by dou x ax plus dou by dou y ay plus dou by dou z az. That what I write directly here, that is dou v by dou x ax plus dou v by dou y ay plus dou v by dou z az. Now what we have to do is we have to integrate this particular function with respect to x, with respect to y and with respect to z once. So for x component, so z add the unit vector ax, for y add unit vector ay, for z add unit vector az. Now just differentiation will be taken directly. Directly I am differentiating that one. So which is equals to minus, if you differentiate this one with respect to x, for the first one what we get is y square z cube. For this particular term it is y square z cube, and for logarithmic function what we have is 3 by 2, it's in the denominator, it's 1 by x square plus 2y square plus 3z square, and the internal differentiation of this one is 2x. So that is dou v by dou x is this entire term with ax plus next dou v by dou y. This v function will be differentiated with respect to y. So if you differentiate this one with respect to y, what we get? Just it is x 2y z cube. So it is simply 2xy z cube plus, for the second term if you take the differentiation, what we get is 3 by 2, and once again it is log function. Therefore in the denominator what we get is x square plus 2y square plus 3z square, and the internal differentiation will give us 4y, that will be in the numerator. This is our second term plus the third term. The third term what we have is the differentiation is with respect to z. So the differentiation with respect to z for the first time is 3xy square z square, that is for the first term, and for the second term plus 3 by 2, and in the denominator since it is once again it is a logarithmic function, so with respect to z x square plus 2y square plus 3z square, and in the numerator the internal differentiation is 6z. So this is the total function what we have, that the gradient of the potential, that the gradient of potential is nothing but the electric field intensity. Now clearly observe, I forgot to write down the unit vectors here. For the first term the unit vector is ax, and for the second term for the dou v by dou y the unit vector here is ay, and for the third term dou v by dou z the unit vector here is az. Now clearly observe, so using our potential, so what we got is this particular entire expression. Now the electric field intensity will be calculated at 3, 2, minus 1. So what we have to do is instead of x substitute 3, instead of y substitute 2, instead of z substitute minus 1. So using a calculator, after substitution we will get a simplified value that for electric field intensity in terms of ax, ay, az. That is the solution for that one. After calculation of the electric field intensity, we have to obtain the electric flux density. Already we know the electric field intensity and the electric flux density are related with the simple equation that D is equals to epsilon naught E. Since this V is given in free space, we are considering that one as epsilon naught. Therefore, after getting the equation or after getting the some value what we are calculated using our calculator, multiply that one with epsilon naught. Right? If you multiply that one with epsilon naught, what we get is D. But don't forget to write down the units. The electric field intensity units are volt per meter, and what are the units for D? That are coulomb per meter square. So this is a simple solution. So nothing more than that. Applying the gradient for the potential equation, we will get the electric field intensity directly. So this is our answer. Problem 10. A 50 microcoulomb charge is located at the origin. then the total electric flux passing through the hemisphere surface defined by r equals to 48 meter, 0 less than or equals to theta less than or equals to pi by 2 is dash microcoulomb. Solution to this problem. Just observe what is the data given to us. A charge q is equals to 50 microcoulomb was placed at the origin and a hemisphere was defined with radius is equals to 48 meter and for the given theta is equals to 0 to pi by 2. Now we need to calculate the total flux passing through this particular hemisphere. For that, what we do is try to interpret the data and try to represent that one as a picture. Here let us take this is a coordinate system, base coordinate system what we have, and the hemisphere was represented with radius is equals to 48 meter and the theta is from 0 to pi by 2 only. Since it is hemisphere, only half of the sphere will be considered. So with radius 48 meter, a hemisphere what we are drawing here, let us take this is the hemisphere what we are supposed to consider. The lower half of the sphere is not there, that it's not given, right? A charge q was placed exactly at the origin with some value 50 microcoulomb. Now we need to calculate the total flux passing through the sphere. For that, observation is required here, no more calculations, nothing. Now if you identify so what is there, then easily you can answer this one. The charge is there, a simple point charge is there, that because of this point charge definitely some flux will pass us through the surface what we are considering. Let us take or let us assume the surface what we are considering is a complete sphere. So this is the complete sphere what I am taking. So because of that charge, what is the flux passing through that one? Using our Gauss law directly you can relate the flux and charge as the total flux passing or leaving is equals to the charge enclosed. So simply what you can say is the total flux passing through the complete sphere what we have here is charge, that is nothing but 50 microcoulomb. So the total flux leaving is equals to just 50 microcoulomb. But here what we require is the flux passing through only half of the sphere, that is for hemisphere. So clearly from that representation or observation you can say that only half of the flux will pass us through the upper sphere, the remaining half will be passed through the lower sphere. Since we have no lower sphere, just half of the flux which will pass us through the upper sphere is the answer. That is, the flux passing through the upper hemisphere is equals to half of the original one or total one, that is 50 microcoulomb divided by 2 which is equals to 25 microcoulomb. This is our answer. So with the observation you can say, and if the same problem was asked like this, only quarter part of the sphere is given to us, then the answer is 50 divided by 4. If 3/4 of the sphere is given to us, then it's 50 divided by 4 minus 50 divided by 1/4 of this particular value. Like that what we have to do is we have to divide the entire flux according to the requirement. So since it is half of the sphere, only half of the flux will pass through it. So if 3/4 is given, 3/4 of the flux will pass through that particular quantity what we have. So this is the solution for this question. Problem number 11. If the electric field intensity is given by E is equals to x ax plus y ay plus z az volt per meter, the potential difference between a point x 2 0 0 and another point y 1 2 3 is what? Solution. So here clearly what we are supposed to calculate is the potential. What is the given data is electric field intensity. Already we know that there is a clear relation between the electric field intensity and this potential. So here once again remember that this is not potential, it's a potential difference. So we are supposed to calculate the potential difference between 2 points, that this is a point 1 and this is a point 2. Just represent that one as a picture, right? So let us take this is one point P, it's a x is given as 2 0 0 and another point y is given like this with coordinates 1 2 3. Don't go for any coordinate system, just we are representing the point. Now between these two, what will be the potential difference when the electric field intensity is given to us? That what we require is Vxy. So what is Vxy potential difference between them, right? Now what is the basic relation between the V and E? So we have a basic relation, potential difference is equals to minus line integral of E dl. That what we have, right? This line integral will be calculated from the first point to the second point. Always recollect the concept what we have. This line integral will be taken from the starting position to the ending position. So what I write down this one is, it's a minus this from point x to the point y integral E dl. That what we have. Now replace this E with the equation what we have, and replace dl with the equation what we are supposed to take in rectangular coordinate system. In the Cartesian coordinate system, since this is given in Cartesian coordinate system, take dl in Cartesian coordinate system. How you can write this one? Dx ax plus dy ay plus dz az. So directly take down. So the dot product between this dl and E. So what is the dot product between these two? So if you take ax dot ax1, ay dot ay1, az dot az1. So after taking the dot product and substitution here, directly I am substituting. Just v can be written as minus integration is from point x to point y. And if you take the direct dot product, what we get is x dx plus y dy plus z dz. This is a simple equation what we get, right? Now how to obtain this particular integration? To obtain this particular integration, we need to substitute the limits. The limits for x, the limits for y, and the limits for z we are supposed to take. So what I do is, I'll divide this entire integration. Now the x value is from, the x is varying from, the x coordinate is from 2 to 1. So x will be taken from 2 to 1 and the integral is now x dx plus the y will be taken from, the y coordinate will be taken from 0 to 2. So it is from y is equals to 0 to 2 y dy plus the third one is for z. Z will be taken from 0 to 3. So the integration for z is from 0 to 3. It is z dz. So just the simplification of this one will give us the answer. That is the potential difference for this particular quantity. So what we are taking from point x to point y can be calculated using its electric field intensity with this simple integration. So what we get here, which is equals to minus the integration of x is x square by 2, the for limits are from 2 to 1, plus for y also it is y square by 2, it is from 0 to 2, plus z square by 2, that is from 0 to 3. Now simplify this one. So which is equals to minus, I will take this 1 by 2 common, then here 1 by 2 minus 4 by 2, that is minus 3 by 2, that what we get, 3 by 2, 2 is over, right, minus 3, that what we get here, minus 3, plus for the second term 4 minus 0, just what we get is 4, for the third term 9 minus 0, that is plus 9, what we get. So this is simply 13 minus 3, 10, 10 by 2, which is equals to minus 5 volts. This is our answer. So clearly this potential difference between the 2 points x and y can be calculated using our electric field intensity equation. So by substituting this simple formula, this is the solution. Problem 12. If potential distribution is given as v equals to 10 y power 4 plus 20 x cube, and if epsilon naught is the permittivity of free space, what is volume charge density rho v at a point 2, 0? Here the potential is given to us. So the potential is given as 10 y power 4 plus 20 x cube, that may be given in volts, and we require the volume charge density using this potential. How to obtain the volume charge density from the potential? First what we have to do is try to correlate them with the equations what we have earlier. For that, try to relate this v with e, e with d, d with rho v. That may be a little bit convenient one. So how to relate this v with e? So already we know electric field intensity is equals to minus gradient of v. So that's the equation, that's the relation between E and V. Now E can be related with D, as D is equals to epsilon naught E. Since it is given in free space, you can write that one as epsilon naught E. And we have a relation between this D and rho V, that from our classic law, that is our Gauss law, del dot D is equals to rho V. So volume charge density can be calculated using this D, but we have no D. Instead of D, what we have is E, but E can be calculated from the potential V. So substitute in that particular equation only. So if we substitute in that particular equation, then instead of D I can write del dot epsilon naught E is equals to rho V. That what I can write. Since epsilon naught is taken for free space, bring it out from the del operator, that is epsilon naught del dot E is equals to rho V. That what we can write. Now instead of this del dot E or instead of this E, what I can write is minus gradient of V. Substitute minus gradient of V here. That is del dot minus gradient of V is equals to rho V. That what we have. So del dot del V, simply directly you can replace this one with del square V, and the negative sign comes this side. Minus epsilon naught del square V is equals to rho V. Therefore clearly del square V is equals to rho V by epsilon naught minus rho V by epsilon naught. This is one of the relations we know, we are supposed to remember. But don't go this relation, just we must stop here. That is rho V, the total volume charge density can be obtained from potential using this simple relation, that rho V is equals to minus epsilon naught times of del square of V. This del square operator is a Laplacian operator. So apply this del square on our potential equation. How to apply this del square operator? Just we need to take the del square operator in the respective coordinate system. Here the coordinate system is a rectangular coordinate system. Even though there is no z term, just treat this one is as a rectangular coordinate system. So what I am doing is I am trying to apply this del square operator on V. That is del square V I am trying to calculate. That is dou square by dou x square of V plus dou square by dou y square of V. So 2 times you need to differentiate this one. Twice you have to differentiate this, which is equals to dou square by dou x square of what is V here? 10y power 4 plus 20x cube plus the second term is dou square by dou y square of 10y power 4 plus 20x cube. Clearly remember, this is a scalar quantity, is not a vector quantity. There will be no unit vectors here. So this term becomes 0, and twice if you differentiate this one, 20 into 3 60 x square, that is the first time. And so once again if you differentiate this one, that is 60 into 2 120x. So which is equals to 120x. That is for this particular term. So once again 20 into 3 60 x square and 60 into 2 120x, plus for the second term, since it is taken for the y, these terms will be cancelled and 40y cube, and the latter it will become 40 into 3 120y square. So it is 120y square. So simply this is the equation for del square V, but what we require is minus epsilon naught del square V for rho V. Therefore now rho V is equals to minus epsilon naught times of 120x plus 120y square. This is a simple value. What are the units of this one? Coulomb per volume charge density meter cube. But this rho V will be calculated at a point x is equals to 2, y is equals to 0. So substitute x equals to 2 and y is equals to 0 here. Then the equation, the value for this rho V at 2, 0 now becomes x at 120 into 2, it is minus 240 epsilon naught plus this term becomes 0 coulomb per meter cube. This is our answer. So just simply what we have to do is we have to correlate what is the given data to us. So potential is given to us. Using that potential we are supposed to calculate the volume charge density. So the volume charge density and the potential will be related with this particular expression. So this is a very simple one and solution for our problem.